This is Borna, your organic chemistry tutor. I've been a teaching assistant for a few years now, and I've seen plenty of students who struggle with organic chemistry but cannot afford to hire a tutor. I started this channel to distribute quality educational material and help create equal opportunity for everyone. So if you support my cause, please like, share, and subscribe. Thank you so much.
So this is generally speaking true. In acid catalyzed reactions or in acidic environments, you'd like to avoid having negatively charged species as much as possible. And as opposed to making your nucleophiles better nucleophiles by deprotonation, usually make your leaving groups better leaving groups by protonation. On the other hand, in acidic in basic environments, usually what is going to happen is that you're going to have a buildup of negative charges. You're going to create better nucleophiles from your nucleophiles as opposed to making your electrophiles more electrophilic. The product of this reaction is going to be this. And now, like with that said, it is not going to be reasonable to have a negatively charged nucleophile under acidic conditions. Before I get into the mechanism slightly deeper, I'd like to try to figure out what the connectivity is like. So let's number the carbons. So 1, 2, 3, 4, 5, 6, 7. Okay, so I tend to think that it's likely under these conditions for a nucleophilic attack on the epoxide to occur because we are under acidic conditions. We can protonate the epoxide that will enable even weaker nucleophiles to attack the epoxide. So I tend to think that is probably what is going to happen. I also have an internal double bond nucleophile, but that is not immediately what I can see in the product. So let's not get too caught up on that. But with that said, I'm likely to think that the oxygen is going to end up on one of the carbons of the epoxide. In other words, I'm likely to think, like I tend to think that this is probably carbon 7, this is probably carbon 6. This kind of does make sense, like something having attacked the 7th carbon of the epoxide, leaving the oxygen on carbon 6. And then after 6, there's 3 CH2, so they're likely to be 5, 4, 3. And then 2 and 1 are likely to be these two. And whenever I feel like I have done the numbering wrong, I can always go back. Like, it's not a problem. Okay, so what has happened is that seemingly the double bond is not touched, and then the epoxide has been opened, and a bond between carbon 2 and carbon 7 has been made. So if I make a table of the bonds that are broken and made, that helps me kind of think about what is logical to happen under these conditions. So the bonds that are broken are carbon 7 like oxygen. That makes sense. That is consistent with something having attacked the epoxide. That makes sense. And the bonds that are made are carbon 2, carbon 7. Okay. So under acidic conditions, as I said, we can protonate the epoxide. That makes a lot of sense. And also it does make sense for my double bond to act as a nucleophile towards the now activated epoxide. And I know that that needs to happen such that a bond is created between carbons 2 and 7. And just so I don't get confused, 1, 2, 3, 4, 5, 6, 7. So there's going to be a ring consisting of carbons 2, 3, 4, 5, 6, 7, which is 6. So I'm going to draw a 6-membered carbon only ring. So 2, 3, 4, 5, 6, 7. On carbon 7, I'm going to have two methyls like this. On carbon 6, I'm going to have an OH. On carbon 2, I'm going to have an isopropyl with a positive charge on it, and that totally does make sense. Now, the only thing that needs to happen is that this compound or intermediate needs to lose a proton to go to the product. And despite the fact that this looks slightly different than what we have, it's the same compound. It's a 6-membered ring with a dimethyl on it between a hydroxy and an isopropylene group.